So what we're going to do is we're just going to take these two definitions here, and then we're going to go check something out online real quick. All right, so I'm going to go to, let's see. I'm just going to go to I'm going to go to my website, and you guys can. It's coming back. On my website, there's a link right here. You guys are welcome to check that out. Okay, but that's going to be mutually. It goes here, I hope. All right, this is on that Math is Fun website. It's a fantastic website. Now, I really like the mutually exclusive. If you'll check this out, they've got a really great definition, really great examples of when things are mutually exclusive and not. Mutually exclusive things cannot happen at the same time. Okay, it's that simple. These are some great examples. You cannot turn left and right at the same time. They are mutually exclusive. One prohibits the other. You cannot jump up and jump down at the same time. Okay? You cannot breathe in and breathe out at the same time. Okay? Whoa.
Those idiot people came
Wait.
and they're running
Yes. Do you remember?
I know what you're talking when they like sit like this and they have
Yes. Oh my God. I so remember that.
I remember that too.
Oh my God.
And they don't use the word inclusive, but by saying not mutually exclusive, I'm saying they're inclusive. Okay, so on your notes it's
Is
inclusive.
that a word?
It is. You can turn left and scratch your head at the same time. That can happen. Okay? And then more practically, you can have the king, you can have a king and a heart at the same time because there is a king of hearts, right? So they give you some good examples here. Let's look at this Venn diagram real quick because it's a great Venn diagram. Notice in this particular one on the left, there are 4 aces in a deck and there are 4 kings in a deck. These are mutually exclusive events because you cannot be an ace and a king at the same time. There is no card in the deck that is an ace and a king at the same time. They're mutually exclusive. How many aces or kings are there in the deck? Say that again. How many aces or kings are there in the deck? There are 4 aces and there are 4 kings. There are 8 aces or kings, right? All right, that's mutually exclusive. Pretty straightforward. Just add them up, right? Pretty straightforward. Now over here, though, excuse me, over here, you got a great picture that shows every single heart in the deck. How many hearts are there in a deck? 13. You have the picture that shows all the kings in a deck. How many kings are in a deck? 4. So is it natural to think that 13 plus 4 would give you 17 hearts or kings? Why doesn't that work?
Because there's a king of hearts that goes into both.
All right. Right here, there's an intersection, and you actually counted the king of hearts twice. You counted it one time when you said 13, and you counted it again when you said 4. So this really doesn't work. If you count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's only 16 cards that are hearts or kings. So the answer can't be 17. It has to be 16. And how do I get that? I subtract the 1 king that they both have in common. And that's where we're going to look at our definition. All right? All right. So we're looking at the exclusive and the inclusive. What I want to do is I want to look at a deck of cards, the probability of an ace or a 10. Are these two events exclusive or inclusive? They are exclusive because it is impossible to have a 10 that is also an ace. These are exclusive, right? So because they're exclusive, I need to use the exclusive formula up here. I'm just going to add the two probabilities together. Because this says or, and or means union, right? Okay, so what is the probability of that ace? 4 out of 52, right? And what's the probability of that 10? Also 4 out of 52. I'm going to add them together. Now I'm lucky, I got common denominators. It's going to be 8 out of 52. That's no surprise, right? And you can go ahead and round that for me. What is that? All right, so it's about 15%. Now let's go over here and look at the ace or a heart. What's different about this problem?
Period, out of ace and hearts.
Okay, ace or a heart. Don't forget that's a U. Ace or a heart. These two things can happen at the same time, can't they? These are inclusive. So because it's inclusive, I have to use my inclusive formula. I have to still add the two probabilities together, but then I'm going to subtract whatever they have in common. So what's the probability of that ace? 4 out of 52. And what's the probability of that heart? Well, there's 13 hearts, right? So 13 out of 52. But somewhere inside both of these, I've double counted, haven't I? So I need to subtract what they have in common. How many ace hearts are there? There's one ace heart, right? So I'm going to subtract 1 out of 52. And when you put that together, you got 4 plus 13 minus 1. And of course, that's 16 out of 52. And that is... I'm going to clear these out, and I'm going to look at those other two. I should have gave myself a little bit more room, I guess, for this next problem. All right, so we're going to roll a die this time, singular of dice. I need to know the probability that I get an odd or I get a 6. So think about that. That's an odd. I can have an odd or a 6. Now, can they both happen at the same time? So these are exclusive. So I'm just going to add them up. So this is exclusive. So the probability of an odd is 3 odd numbers out of the 6 on the die. And the probability of a 6 is 1. There's only one number 6 on the whole die, right? So 3 6 plus 1 6 is 4 6. And of course that reduces down to 66%, 67%, right? All right. Now let's look over here at this second situation. Probability of an even or a number bigger than 3. Can those both happen at the same time? Yeah. Yes, so this is inclusive. So I have to remember if it's inclusive to get rid of the overlap. So how many evens are there? 3 out of 6 on the die. And how many numbers are bigger than 3? Well, there's also 3 out of 6. 4, 5, and 6, right? So there's 3 out of 6 that are bigger than 3. But where do they overlap? Okay, if you need to write them down, write them down. But what numbers are bigger than 3 and even? Uh-oh. These two, right? So there is minus 2 out of 6. So 3 6s plus 3 6s minus 2 6s ends up giving me 4 6s, which, hey, look, it's the same answer. By coincidence. All right, so we went ahead and totaled up all of our columns and all of our rows and the total, just in case we needed that information. Now let's look at this. It says the probability that I'm a freshman or a sophomore. A freshman or a sophomore. Think about that. Is that mutually inclusive or exclusive? That's exclusive. You cannot be a freshman and a sophomore at the same time. So this is mutually exclusive. So if it's exclusive, I need to do the freshman, which is 276 out of 1180, plus the sophomores, which was 284 out of 1180. And I think actually we did that yesterday, but we didn't talk about why we were doing it. We just added them up, didn't we? It's pretty much common sense, isn't it? Add up all the freshmen and sophomores. That's what the or means. But that's what our rule is telling us. It tells us to add them. So finish that up for me. What is that?
We have like a.
All right. So that was just, it's 560 over 1180. You add them up and you go. Now what's happening right here? I've got the probability of a junior and a senior. Probability of a junior and a senior. Okay? Are these mutually exclusive or inclusive? Okay, these are going to be exclusive. You can't be a junior and a senior at the same time, right? So I'm going to do, these are exclusive, so just like the last one, I'm going to do the probability of a junior and a senior. But wait a second. This is a intersect sign. It's not a union sign, right? So how many juniors are seniors? You said they were exclusive.
You just stop there.
All right, that's exactly right, and that's actually a rule of exclusive. If you have two events that are mutually exclusive, okay, the probability of a junior and the probability of a senior, if they are exclusive, will equal 0. Okay, it can't happen. Remember, that was the definition of exclusive, is they don't have anything the same. They cannot happen at the same time. So that's an important thing to know. That would be a quick one to answer, but it is important to know. Okay, now you're right. That one is mutually inclusive because aren't there people that are juniors and non-varsity people at the same time? Yeah, these people right here. Let me change my color here. These people right here are juniors and non-varsity people. Okay, so it is inclusive. So I need to go through and I need to use my formula. All right. So I need the probability of a junior plus the probability that I'm a non-varsity player. But I also need to subtract the probability that I'm a junior and non-varsity at the same time. That's what the formula would look like. Now the numbers, you guys are probably better with the numbers. How many juniors were there? Okay, so I've got 312 out of 1180, right? And then how many non-varsities were there? 1,064 out of 1180. I'm sorry that's not showing up very good at the bottom. But what am I going to subtract? All right, I'm going to subtract those that are both juniors and non-varsity, 276 out of 1180. And I have to subtract them because I didn't mean to, but I've already counted them twice. So somebody run those numbers. All right, it's going to be 1,100 out of 1180, and you heard that's about 93%. Okay? Okay? It's very super tempting as you do this, as you look at this problem. I'll give you a second to read that. It's very super tempting to say how many people are in both classes together. How would I write both classes together, by the way? How would I write, not B. How would I write, this is what I want. Let me rephrase that. I want to know what people are here. Okay? I want to know how many people are in all of this together, this yellow. Now notice that where I drew the yellow. I didn't, okay? So I want to know how many people are in math or science. That looks like math or science. How many people are in math or science? What's it tempting to say? It's tempting to say there are 335 people in math, 287 people in science. Is that right? Okay. And some people might even say the 220. But what happens when you add that up? Right. This gives us 842, and that can't possibly be true because there's only 540 people in the whole school. So something's wrong. Most people would realize, hey, I don't need to count that 220. I'm really only talking about math and science. So when you add those two together, you end up with this. What is that? 622. But what's wrong with that?
You guys try to hit me.
Yeah. That still shows you too many people, doesn't it? What happened was this. You counted this 220 twice. That 220 is already part of the 335, and it's also part of the 287. So what you have to do is you have to subtract the 220. And now, what does that look like? It looks like this. Remember. Oh, I forgot about those. Still left that. It looks like this, guys. Remember, it's going to be M plus it's going to be S. And then it's going to be minus M and S. Okay? Just like on our mutually inclusive. So we've got what I just wrote down. We've got 335 plus 287. But we have to subtract the people that we accidentally counted twice. And that's counting 220 of those. And what does that end up being? How many students? So there ends up being 402 students in either math or science. Math or science. Well, where are the rest of them? All right, that's a good question. That's actually what I wanted to know, right? How many students take neither? If there's 540 in the whole school, remember that big box told us that there's 540 in the whole school right here. And everything inside the yellow is 402, then I could subtract them. So down here, who's not in math and science? It's going to be 540. Subtract that 402. And how many people are in not math or science? 138.
Those are the lucky ones.
Okay? You call those poor, unfortunate souls. All right, so in a certain class with 40 kids, 18 students prefer classical, 24 prefer jazz, while 8 have an equal preference for both. What's the probability that a randomly selected student prefers neither? So I am asking you a probability question, okay? But before I can even do that, I need to know how many is the neither, okay? Venn diagram is where I need to go with this. So let's see what we can do with that.
Whoa, how'd you make it perfect?
It's because I'm that good.
That is not perfect.
You ruined it.
All right. All right. So I've got classical music. I've got jazz music, right? And how many are in the whole class? Okay. And there's 40 in the whole class. What's the probability that a random, let's see. How many students prefer classical? 18. So this circle has 18 students in it. Now some of those students are over here, and some of those students are over here, but altogether it has 18 students. How many prefer jazz? 24. Same idea. Some of these students are on the right part of the circle, and some part are on the intersection. Okay? How many students have an equal preference for both? 8. And they're going to be the intersection. So my question for you is, what's the probability that a randomly selected student prefers neither? Well, do you know what I think I'm going to find first? I think I'm going to find the probability that they are in one of the two circles, right? So they are either classical or jazz. So are these events mutually exclusive or inclusive? These are inclusive. This is an inclusive situation because clearly they have overlap, right? So there are some people that are in both, so this is inclusive. So I'm going to do the probability that they're in classical. I'm going to add the probability that they're in jazz. But I'm going to subtract any that are in classical and jazz at the same time. So that's going to be minus the probability that they're in classical and jazz. I know that got a little sloppy, so make sure you can see that. Probability of classical and jazz. All right, so what is the probability I'm in classical? Good. There are 18 that like classical out of 40 in the class. Plus those students that like jazz. 24 out of 40. Minus those that like both, which is minus 8 out of 40. So go ahead and run that number.
26.
All right, so it ends up being 34 out of 40, which is 85%. But does that answer my question?
No.
I wanted to know how many preferred neither. This represents how many preferred classical or jazz. So what would neither be?
15.
All right. Neither would be
15% of 40, which is
classical or jazz. It'd be the opposite of that, right? It'd be the complement, so it's going to be 15%. It's going to be what's left over.